This movie deals with waves. It is intended for viewing before students do a laboratory experiment designed to illustrate the creation and determination of wavelength, speed, and frequency of standing waves. Upon completion of the laboratory activity associated with this movie, students will be expected to be able to define and describe simple harmonic waves, describe a standing wave and explain how a standing wave is created, and determine the wavelength, speed, and frequency of a standing wave. A wave may be defined as a transfer of energy from one point to another. For example, suppose you drop a rock into a pond of still water. You create a disturbance which moves or propagates away from the source of disturbance. It is important to note that it is the disturbance that is propagating, not matter. In fact, this is what makes waves important. They transport energy without the transport of matter. Consider the wave represented in the plot shown here. As drawn here, the wave is propagating toward the positive x-axis. You can imagine the red curve as string that is continuously being moved up and down at one end in a simple harmonic manner. Look closely at what the string is doing 1 centimeter away from the source of disturbance. That is, look at the point marked by the circle at x equals 1. It's not moving to the right. It's simply moving up and down. The wave being illustrated here is an example of a transverse wave. Matter oscillates in a direction perpendicular to the propagation of the disturbance. In the example here, the string moves up and down at every point, while the wave moves to the right. You might find it useful to imagine the red curve as representing a wave on water. The circle at x equals 1 could be a cork that's bobbing up and down, suggesting that the water itself is not moving to the right. Frequently, the disturbance which produces a wave is simple harmonic. In this case, the wave can be described by a sine or cosine function of time and location. Consider the example shown here. The mathematical function describing the wave as a function of location and time is a cosine omega times t minus k times x, where a, omega, and k are constants. What do you think is the value of a for the plot shown here? We know that a cosine function ranges from positive 1 to negative 1. Therefore, we expect the maximum to be positive a and the minimum to occur at negative a. A is called the amplitude of the wave. It would be easier to interpret omega and k if we express them in terms of things we can use to describe the wave. It can be shown that k equals 2 pi over lambda, where lambda is the wavelength. We say that the disturbance completes one cycle when it has traveled one wavelength. The pattern repeats again and again after that. The wavelength simply refers to the distance between adjacent peaks. What do you think is the wavelength of the wave shown here? The wavelength can be easily determined from the plot by determining the crest-to-crest distance, or the trough-to-trough distance. The wavelength here is 2 centimeters. As for omega, it can be shown to be equal to the period, tau. The period, tau, is the time it takes for the disturbance to complete one cycle. In other words, it's the time it takes for the disturbance to travel one wavelength. The plot you see is a snapshot of the wave at time 0. Watch what happens as time, shown here in seconds, advances. Estimate the period of the wave. It takes 1 second for the wave to advance by one wavelength. Therefore, the period is 1 second. The frequency of the wave, f, is the number of cycles that pass through a point per unit time. It's equal to the reciprocal of the period. That is, f equals 1 over tau. In the example shown here, f is 1 cycle per second, or 1 hertz. How fast is the wave propagating to the right? You will recall that speed is the distance traveled per unit time. Know that the wave takes one period to travel a distance lambda. Therefore, speed equals distance traveled, lambda, divided by elapsed time, tau. Since frequency is the reciprocal of the period, tau, the speed of the wave is also equal to lambda times f. You should also be able to show that the speed is equal to omega over k. In reality, a traveling wave will eventually encounter a boundary where it will be reflected. If the boundary is rigid, the wave will be inverted as it is reflected. Examine the snapshot of the traveling wave shown here in red and blue. Imagine the wave as representing a string that is being moved up and down at x equals 0. Imagine that the wave encounters a rigid boundary at x equals 5. Watch carefully. You will note that the red curve represents the wave propagating to the right. The blue curve represents the reflected wave. Note that at x equals 5, the red and blue curves are exactly opposite. The same would be true at x equals 0, where the reflected wave will be reflected back. The black curve shown here is the sum of the blue and red curves. You would only see this if the distance between the boundaries, L, is equal to an integer multiple of lambda over 2. We get what is called a standing wave. If L is not an integer multiple of lambda over 2, we do not get a standing wave. If the frequency is really high, imagine the black curve oscillating really fast. All you would see is a blur in the shape shown in the bottom figure. One thing you will note about standing waves is that there are places where the string remains stationary. These are called nodes. Between the nodes are points where the string moves fastest. These are called antinodes. The number of antinodes is equal to n, where n is the integer multiple mentioned earlier. If there are n antinodes, then there are n minus 1 nodes between the boundaries. Including the boundaries, there are n plus 1 nodes. The speed of a wave depends on the material where the disturbance is propagating. In the case of a wave on a stretched string, it is found that the speed depends on two factors: the tension on the string, F, and the linear density, m over L. Tension refers to the force that tends to stretch the string. When the tension is greater, we expect the speed of propagation of the disturbance to be faster because each segment of the string would be in tighter contact with its neighbor. Linear density refers to the mass per unit length. A higher density implies more mass per unit length, that is, more inertia. The segments in the string would be more resistant to changes in motion. Hence, a higher linear density implies slower propagation. Mathematically, the relationship is found to be given by the equation shown here. The speed, v, is equal to the square root of the ratio of the tension, F, to the linear density, m over L. Consider the following example. What is the speed of a wave traveling down a wire if the wire is 150 meters long, has a mass of 15 kilograms, and is under a tension of 200 newtons? The linear density is 15 kilograms divided by 150 meters, or 0.100 kilograms per meter. The speed of the wave, v, is equal to the square root of the force, 200 newtons, divided by the linear density, 0.100 kilograms per meter, or 44.7 meters per second. Here's an overview of the experiment we will be doing in the lab. We will create standing waves on a string by tying a string on one end to an electrically driven vibrator. The vibrator will be oscillating left and right and is the source of the disturbance. We will stretch out the string over a pulley which will serve as the other boundary for the wave. Measure the length of the string between the tip of the vibrator and the point where it touches the pulley. We will set the tension on the string by hanging weights on it. The force of gravity on the hanging weights is equal to the tension on the string. We will adjust the hanging weights so that we can get a standing wave similar to the one pictured here. Determine the weights needed to get 2 antinodes, 3 antinodes, 4 antinodes, 5 antinodes, and 6 antinodes. When recording your data, be sure to include the mass of the hanger. Finally, cut off 1 centimeter length of string and weigh it in order to determine the linear density of the string. Here's what you need to do with your data. For each standing wave, calculate the wavelength, tension on the string, the speed of the wave, and the frequency of the vibrator, F. You will recall that we get a standing wave whenever L, the length of the string, is an integer multiple of lambda over 2. The integer, N, is simply the number of antinodes. Therefore, we have all the information we need to calculate the wavelength. The wavelength is equal to 2 times L divided by N. The tension on the string, F, is equal to the force of gravity on the hanging weights. Simply multiply the total mass hung from the string, including the hanger, by g, which is the acceleration due to gravity. The speed of the wave is equal to the square root of the ratio of the tension to the linear density. Finally, we can calculate the frequency of the vibrator. Recall that the speed is equal to lambda times f. Therefore, f is equal to v over lambda. The frequency of the vibrator is fixed, so it should come out more or less constant for all the standing waves. Try to relate your experimental value to the fact that your vibrator is driven by alternating current, which has a frequency of 60 Hz. An alternative approach to determining the frequency of the vibrator is to plot the tension versus the square of the wavelength. You should be able to show that the plot is a straight line, with a slope equal to the frequency squared times the linear density. Therefore, the frequency is equal to the square root of the ratio of the slope to the linear density.